Hello, welcome to our channel. This is the first freshman chemistry course tutorial. It covers the introduction to chemistry, chemistry in context, chemistry as a central science, the scientific method, domains of chemistry and states of matter. We hope you will find this a great addition to your studies. Now, without further ado, let's begin the course. Throughout human history, people have tried to convert matter into more useful forms. Our Stone Age ancestors chipped pieces of flint into useful tools and carved wood into statues and toys. These endeavors involved changing the shape of a substance without changing the substance itself. But as our knowledge increased, humans began to change the composition of the substances as well. Clay was converted into pottery. Hides were cured to make garments, copper ores were transformed into copper tools and weapons, and grain was made into bread. Humans began to practice chemistry when they learned to control fire and use it to cook, make pottery, and smelt metals. Subsequently, they began to separate and use specific components of matter. A variety of drugs such as aloe, myrrh, and opium were isolated from plants. Dyes, such as indigo and Tyrian purple, were extracted from plant and animal matter. Metals were combined to form alloys. For example, copper and tin were mixed together to make bronze, and more elaborate smelting techniques produced iron. Alkalis were extracted from ashes, and soaps were prepared by combining these alkalis with fats. Alcohol was produced by fermentation and purified by distillation. Attempts to understand the behavior of matter extend back for more than 2,500 years. As early as the 6th century BC, Greek philosophers discussed a system in which water was the basis of all things. You may have heard of the Greek postulate that matter consists of four elements: earth, air, fire, and water. Subsequently, an amalgamation of chemical technologies and philosophical speculations was spread from Egypt, China, and the Eastern Mediterranean by alchemists, who endeavored to transform base metals such as lead into noble metals like gold, and to create elixirs to cure disease and extend life. From alchemy came the historical progressions that led to modern chemistry, the isolation of drugs from natural sources, metallurgy, and the dye industry. Today, chemistry continues to deepen our understanding and improve our ability to harness and control the behavior of matter. Chemistry is sometimes referred to as the central science due to its interconnectedness with a vast array of other STEM disciplines. STEM stands for areas of study in the science, technology, engineering, and math fields. Chemistry and the language of chemists play vital roles in biology, medicine, materials science, forensics, environmental science, and many other fields. The basic principles of physics are essential for understanding many aspects of chemistry, and there is extensive overlap between many sub-disciplines within the two fields, such as chemical physics and nuclear chemistry. Mathematics, computer science, and information theory provide important tools that help us calculate, interpret, describe, and generally make sense of the chemical world. Biology and chemistry converge in biochemistry, which is crucial to understanding the many complex factors and processes that keep living organisms alive. Chemical engineering, materials science, and nanotechnology combine chemical principles and empirical findings to produce useful substances, ranging from gasoline to fabrics to electronics. Agriculture, food science, veterinary science, and brewing and wine-making help provide sustenance in the form of food and drink to the world's population. Medicine, pharmacology, biotechnology, and botany identify and produce substances that help keep us healthy. Environmental science, geology, oceanography, and atmospheric science incorporate many chemical ideas to help us better understand and protect our physical world. Chemical ideas are used to help understand the universe in astronomy and cosmology. Digesting and assimilating food, synthesizing polymers that are used to make clothing, containers, cookware, and credit cards, and refining crude oil into gasoline and other products are just a few examples. As you proceed through this course, you will discover many different examples of changes in the composition and structure of matter, how to classify these changes, how they occurred and the principles and laws involved. As you learn about these things, you will be learning chemistry, the study of the composition, properties, and interactions of matter. The practice of chemistry is not limited to chemistry books or laboratories. It happens whenever someone is involved in changes in matter or in conditions that may lead to such changes. Chemistry is a science based on observation and experimentation. Doing chemistry involves attempting to answer questions and explain observations in terms of the laws and theories of chemistry, using procedures that are accepted by the scientific community. There is no single route to answering a question or explaining an observation, but there is an aspect common to every approach. Each uses knowledge based on experiments that can be reproduced to verify the results. Some routes involve a hypothesis, a tentative explanation of observations that acts as a guide for gathering and checking information. A hypothesis is tested by experimentation, calculation, and/or comparison with the experiments of others and then refined as needed. Some hypotheses are attempts to explain the behavior that is summarized in laws. The laws of science summarize a vast number of experimental observations, and describe or predict some facet of the natural world. If such a hypothesis turns out to be capable of explaining a large body of experimental data, it can reach the status of a theory. Scientific theories are well substantiated, comprehensive, testable explanations of particular aspects of nature. Theories are accepted because they provide satisfactory explanations, but they can be modified if new data become available. The path of discovery that leads from question and observation to law or hypothesis to theory, combined with experimental verification of the hypothesis and any necessary modification of the theory, is called the scientific method. The domains of chemistry. Chemists study and describe the behavior of matter and energy in three different domains: macroscopic, microscopic, and symbolic. These domains provide different ways of considering and describing chemical behavior. Macro is a Greek word that means large. The macroscopic domain is familiar to us. It is the realm of everyday things that are large enough to be sensed directly by human sight or touch. In daily life, this includes the food you eat and the breeze you feel on your face. The macroscopic domain includes everyday and laboratory chemistry, where we observe and measure physical and chemical properties such as density, solubility, and flammability. Micro comes from Greek and means small. The microscopic domain of chemistry is often visited in the imagination. Some aspects of the microscopic domain are visible through standard optical microscopes. For example, many biological cells. More sophisticated instruments are capable of imaging even smaller entities such as molecules and atoms. However, most of the subjects in the microscopic domain of chemistry are too small to be seen even with the most advanced microscopes and may only be pictured in the mind. Other components of the microscopic domain include ions and electrons, protons and neutrons, and chemical bonds, each of which is far too small to see. The symbolic domain contains the specialized language used to represent components of the macroscopic and microscopic domains. Chemical symbols, such as those used in the periodic table, chemical formulas, and chemical equations are part of the symbolic domain, as are graphs, drawings, and calculations. These symbols play an important role in chemistry because they help interpret the behavior of the macroscopic domain in terms of the components of the microscopic domain. One of the challenges for students learning chemistry is recognizing that the same symbols can represent different things in the macroscopic and microscopic domains, and one of the features that make chemistry fascinating is the use of a domain that must be imagined to explain behavior in a domain that can be observed. A helpful way to understand the three domains is via the essential and ubiquitous substance of water. That water is a liquid at moderate temperatures, will freeze to form a solid at lower temperatures, and boil to form a gas at higher temperatures are macroscopic observations. But some properties of water fall into the microscopic domain, what cannot be observed with the naked eye. The description of water as comprising 2 hydrogen atoms and 1 oxygen atom, and the explanation of freezing and boiling in terms of attractions between these molecules, is within the microscopic arena. The formula H2O, which can describe water at either the macroscopic or microscopic levels, is an example of the symbolic domain. The abbreviations, G, for gas, S, for solid, and L, for liquid are also symbolic. A. Moisture in the air, icebergs, and the ocean represent water in the macroscopic domain. B. At the molecular level, microscopic domain, gas molecules are far apart and disorganized, solid water molecules are close together and organized, and liquid molecules are close together and disorganized. C. The formula H2O symbolizes water, and G, S, and L symbolize its phases. Note that clouds actually comprise either very small liquid water droplets or solid water crystals. Gaseous water in our atmosphere is not visible to the naked eye, although it may be sensed as humidity. Figure A shows a photo of an iceberg floating in a sea has 3 arrows. Each arrow points to figure B, which contains 3 diagrams showing how the water molecules are organized in the air, ice, and C, in the air, which contains the gaseous form of water, H2OG. The water molecules are disconnected and widely spaced. In the ice, which is the solid form of water, H2OS, the water molecules are bonded together into rings, with each ring containing 6 water molecules. 3 of these rings are connected to each other. In the sea, which is the liquid form of water, H2OL, the water molecules are very densely packed. The molecules are not bonded together. State of matter. Matter is defined as anything that occupies space and has mass, and it is all around us. Solids and liquids are more obviously matter. We can see that they take up space, and their weight tells us that they have mass. Gases are also matter. If gases did not take up space, a balloon would not inflate, increase its volume, when filled with gas. Solids, liquids, and gases are the 3 states of matter commonly found on Earth. A solid is rigid and possesses a definite shape. A liquid flows and takes the shape of its container, except that it forms a flat or slightly curved upper surface when acted upon by gravity. In zero gravity, liquids assume a spherical shape. Both liquid and solid samples have volumes that are very nearly independent of pressure. A gas takes both the shape and volume of its container. A 4th state of matter, plasma, occurs naturally in the interiors of stars. Plasma is a gaseous state of matter that contains appreciable numbers of electrically charged particles. The presence of these charged particles imparts unique properties to plasmas that justify their classification as a state of matter distinct from gases. In addition to stars, plasmas are found in some other high-temperature environments, both natural and man-made, such as lightning strikes, certain television screens, and specialized analytical instruments used to detect trace amounts of metals. In a tiny cell in a plasma television, the plasma emits ultraviolet light, which in turn causes the display at that location to appear a specific color. The composite of these tiny dots of color makes up the image that you see. Some samples of matter appear to have properties of solids, liquids, and/or gases at the same time. This can occur when the sample is composed of many small pieces. For example, we can pour sand as if it were a liquid because it is composed of many small grains of solid sand. Matter can also have properties of more than one state when it is a mixture, such as with clouds. Clouds appear to behave somewhat like gases, but they are actually mixtures of air, gas, and tiny particles of water, liquid or solid. The mass of an object is a measure of the amount of matter in it. One way to measure an object's mass is to measure the force it takes to accelerate the object. It takes much more force to accelerate a car than a bicycle because the car has much more mass. A more common way to determine the mass of an object is to use a balance to compare its mass with a standard mass. Although weight is related to mass, it is not the same thing. Weight refers to the force that gravity exerts on an object. This force is directly proportional to the mass of the object. The weight of an object changes as the force of gravity changes, but its mass does not. An astronaut's mass does not change just because she or he goes to the moon. But her or his weight on the moon is only 1/6 her or his earthbound weight because the moon's gravity is only 1/6 that of the Earth's. She or he may feel weightless during her or his trip when she or he experiences negligible external forces, gravitational or any other, although she or he is, of course, never massless. The law of conservation of matter summarizes many scientific observations about matter. It states that there is no detectable change in the total quantity of matter present when matter converts from one type to another, a chemical change, or changes among solid, liquid, or gaseous states, a physical change. Brewing beer and the operation of batteries provide examples of the conservation of matter. During the brewing of beer, the ingredients, water, yeast, grains, malt, hops, and sugar, are converted into beer, water, alcohol, carbonation, and flavoring substances, with no actual loss of substance. This is most clearly seen during the bottling process, when glucose turns into ethanol and carbon dioxide, and the total mass of the substances does not change. This can also be seen in a lead-acid car battery. The original substances, lead, lead oxide, and sulfuric acid, which are capable of producing electricity, are changed into other substances, lead sulfate and water, that do not produce electricity, with no change in the actual amount of matter. The mass of beer precursor materials is the same as the mass of beer produced. Sugar has become alcohol and carbon dioxide. The mass of the lead oxide, and sulfuric acid consumed by the production of electricity is exactly equal to the mass of lead sulfate and water that is formed. Although this conservation law holds true for all conversions of matter, convincing examples are few and far between because, outside of the controlled conditions in a laboratory, we seldom collect all of the material that is produced during a particular conversion. For example, when you eat, digest, and assimilate food, all of the matter in the original food is preserved. But because some of the matter is incorporated into your body, and much is excreted as various types of waste, it is challenging to verify by measurement.